Yeah, now it is recording. All right. Yeah. So x1, x2, xn, IID normal theta 1, and then prior follow, suppose normal. Let me just take a little bit quicker. Say normal distribution with maybe some distribution, maybe some tau, say tau 1. No, I don't want to use tau. Tau has a different notational use, so I'll just use say mu. Okay. I don't want to screw up my notation. All right. Now, typically, if I have to find posterior distribution, so the posterior will be effectively pi theta given x tilde, which is effectively f of the joint distribution of x tilde given theta, p of pi of theta prior times this integration of this, which if I can write as effectively integrating out, I can write it as m of x tilde. M of x tilde is free from theta, where m of x tilde is integrating over theta, f of x tilde given theta, pi theta, d theta. Now, what we will do, so we have to, in order to solve this pi theta, in order to figure out what this pi theta given x tilde, what distribution it follows, what we have to do, we have to solve this integration. But what we will do, we will, for the time being, we will do a trick. In a sense, we will try to bypass the integration, because end of the day, this is just a normalizing constant. End of the day, it's just a normalizing constant. So if I can somehow figure out this kernel, this is typically known as the kernel. This is typically what we call this m of x tilde, this is typically called the normalizing constant, because remember that normalizing constant, remember that you integrating out the theta entirely, so an x tilde is your data, which behaves like a constant, which, because you are not, if you observe, that is just an observed realized value. So it will, mx tilde will be a constant. And this is typically called the kernel of the density. So kernel of the density. If we can somehow figure out what is the, if the kernel of the density is in a known form, then we are done. Then we don't have to really solve this integration to figure out the normalizing constant, right? Because, so suppose, what I mean by that, suppose if I just write that x to the power a minus 1 and 1 minus x to the power b minus 1, and x is a constant value which takes value between between 0 and 1. Can you tell me what is this? Definitely it's not a distribution, but can you tell me it is a known function, what this known function is? Say a strictly greater than 0, b strictly greater than 0. Any idea?
Beta function.
Yes. This is my beta function, but it is not beta distribution. Remember that. This is not beta distribution. So this is beta function. If I have to convert it to a distribution, what I have to do? I have to integrate it out between 0 to 1, x to the power a minus 1, 1 minus x to the power b minus 1 dx. This will give me, this is typically how where we stop here. We express it as a gamma function, some functional form of gamma function, gamma AB, beta AB. And then we define the beta distribution f of x as 1 over this normalizing constant beta AB sorry, x to the power a minus 1, 1 minus x to the power b minus 1. Right? So you look at beta AB is nothing but this unsolved integration problem effectively. We just not dividing it as a, using it as a normalizing constant. Now, if you solve it, then it will be integrated to 1, and f of x is now, this guy is, we can say that this is the probability density function of beta distribution, right? We will do exactly same thing. We will focus on this. So this beta function is actually the kernel of the beta distribution. Okay. Same thing we will do. We will try to figure out if this kernel of the density, posterior density, is of some known form. If we know this known form, then normalizing of some known distribution, then we know what is the normalizing constant will be. So we don't have to solve the normalizing constant by solving this integration problem. So turns out we will do this algebra right away. Turns out this, if your data, this is typically oftentimes it's called data model, and this is the prior model. And these, if you take both of them Gaussian, turns out that your kernel of the posterior density will also belongs to a known density. And we will see what that density is. So I'll go back to my original color. Okay. So first, what is my joint density? My joint density is product I equal to 1 to n 1 over sigma square root 2 pi e to the power minus half. Actually, sigma is not required because sigma is 1. So so xi minus theta whole square. So what I will do, I'll just erase that sigma. I don't, because sigma is 1 effectively. All right. So this is my 1 by 2 pi to the power n by 2 and e to the power minus half summation xi minus theta whole square I equal to 1 to n. This is the likelihood function. Okay. Very nice. Let's look into the prior function, prior distribution. What is prior distribution? Pi theta follow normal mu1. So pi theta is following normal mu1. So 2 pi to the power half e to the power minus half theta minus mu whole square, because theta follow normal, mu 1. That is my prior distribution. Now let's look into the kernel of the posterior, which is f of x tilde given theta times pi of theta. What is that? That is 1 by 2 pi to the power n by 2 e to the power or exponent of minus half summation I equal to 1 to n xi minus theta whole square times 1 by 2 pi to the power half exponents of minus half theta minus mu whole square. All right, that means this 1 by 2 pi to the power n by 2 and this 2 pi will behaves so this will be like 1 by 2 pi to the power n plus 1 by 2, and then effectively exponent of minus half summation xi minus theta whole square I equal to 1 to n minus, actually let us take common, theta minus mu whole square. All right. So any guess how can we solve this problem? Is it a known distribution? Let us open this. Let us do a little bit more thing. So this is n plus 1 by 2 exponent minus half is as usual. Psi square is theta 2 theta summation xi plus n theta square plus theta square minus 2 mu theta plus mu square. Now 1 by 2 pi to the power n plus 1 by 2 exp e to the power minus half. So summation xi square into 1 to n minus 2 theta. Now summation xi can be written as n x bar plus mu, and this can be written as n plus 1 times theta square. Okay. So this we can write it as 2 pi to the power n plus 1 by 2 exp minus half looks like we can do some arrangement here, and so I think we can write it as times theta times theta, just so let me write it in this way and see if it makes sense. X bar plus mu divided by actually nx bar plus mu, and then there will be a correction factor. The correction factor will be sigma square 1. In this case, it will be 1 by 1 plus n, because both variances are 1. So it will be 1 by, yeah, it will be 1 by 1 plus n. And this whole thing will be square. And then, but at the same time, there will be a variance. The variance will be, so the variance part will be,
so where did this mu square go in this last line? You have 6 terms in the third last line, and then there are 5 terms in the second last line.
So I'm just trying to write it as a plus b whole square formula, but for that I need to readjust this guy.
Right? In the line above it, you have mu square. Where did it go?
Okay, yeah. So this mu square will be here, I think. Correct. So yeah. So that means, yeah, there must be a mu square, correct. So that is why the problem starts. Yeah. Correct. So now it makes sense. Yeah. So summation xi square and the mu square together will solve the problem for me. I want to write it in this format, and then there will be a variance term which will come here from my, which should be, I think, something like this. One by, I mean, this is the typically this behaves like the variance, and should this constant here, typically this constant behaves like the variance of the posterior distribution, and we know that, and that form is the basically the kernel of this entire thing. Like, this is my random variable, this is my mean, and this is the variance. So this is the mean and this is the variance, and this is my random variable. So this functional form behaves like a kernel of normal distribution from, so I'm doing some, sorry about that. So I'm doing some step jumps here. Okay, sorry about that. I have to, I should be able to solve it. If we do some back calculation, probably we will be able to solve this. But overall, we can say that this, what is this? This theta given x tilde follow a normal distribution with posterior mean is this, that some posterior mean given x tilde and some posterior variance of theta given x tilde, and then posterior mean is my Bayes estimator, which is n x bar plus mu by n plus 1, which you can write it like this: n by n plus 1 times x bar plus 1 by 1 plus n times mu. Here also you can see that same kind of behavior as n tends to infinity. Sort of my posterior mean expectation of theta given x tilde converges to sample mean. So my posterior mean, and this is my prior mean, right? So my posterior mean is the weighted average of posterior mean is my Bayes estimator. In this case is Bayes estimator. Posterior mean is the Bayes estimator, and posterior mean is weighted average of sample mean and prior mean. So it will be always between the sample mean and prior mean. And as you see more and more sample, the effect of the prior mean will be washed out and posterior mean will eventually consistent, will become the my basically Bayesian analysis, and the frequentist or the likelihood analysis will become consistent with each other. So this is typically the solution, typically the way what we think of. Now, before we move on, I would like you to I would like to set up an establish a small, discuss a small section before we finish Bayes estimator section. I want to discuss the relationship between likelihood principle and Bayes principle. Likelihood, the relationship between likelihood estimate and Bayes estimate, and what we look, what is my likelihood estimate? Likelihood estimate is theta hat MLE is arc max theta in the theta space L theta x tilde, and what is my posterior mode or Bayes estimator? One of the important Bayes estimator is posterior mode. So posterior mode is theta hat let me use a slightly different notation. I would prefer. Say theta bar oftentimes these are called maximum posterior estimate, which is effectively arc max, where my posterior distribution pi theta given x tilde is maximum. Correct? Now, what is my pi theta x tilde? Arc max over, I will just put this Bayes theorem whole thing, L theta given x tilde pi theta divided by mx tilde. So mx tilde is completely free from theta. So I am going to it will have no impact on my final solution. So I can just, it is might as well something like this, just the kernel. If I can optimize the kernel of the posterior distribution, that is good enough. I don't have to worry about the normalizing constant in the denominator. So I just L theta given x tilde pi theta, correct? Very nice. Next, what I will do, I will look the likelihood. So that means my posterior mode and the likelihood estimates are going to be behave similar, except my likelihood estimates is now little bit um, sort of have some kind of scaling effect by pi theta because of the pi theta. But what is that? What that scaling effect implies, and I'll talk about it right away. So I can remember that my likelihood function is same as arg max theta in theta is log likelihood of theta given x tilde. Okay. Generally, what we do, we try to maximize the log of likelihood. So here also, we can do the same thing. Instead of maximizing the kernel of the posterior distribution, we can try to optimize the log of posterior, which will be something like this. Theta map will be arg max theta of theta. So log of posterior distribution. Now, what is log of posterior distribution? Log of posterior distribution is effectively log of likelihood plus log of prior. And there will be a minus log of m of x tilde, but that's a constant that has no effect. So I'm just ignoring that constant. Okay. So this is my likelihood solution, and this is my base solution or posterior mode. Now what I'm going to do, I'm going to see for normal distribution what it will be. So take this example of normal theta 1 and prior theta 1. So what is my likelihood? This is my likelihood. If I take log of this, what it will be? It will be, take the example of x1 to xn IID normal theta 1 and pi theta follow normal mu 1. What is it? Now, my L theta, my likelihood is 1 by 2 pi to the power n by 2 e to the power minus half summation xi minus theta whole square. Now you take log of L theta given x tilde, which is minus n by 2 log 2 pi minus half summation xi minus theta whole square, I equal to 1 to n. So, and what is my prior? Prior is log of prior theta is minus half log 2 pi minus half theta minus mu whole square. Okay, guys. So if I consider log of pi theta given x tilde.
So,
Uh-huh.
sir, I am a bit confused about the notations here.
Mm-hmm.
In the third line, I think, in fact, in the second line, I think it should be L x bar given theta. Is it?
This one,
Yeah, above this.
this one.
Yeah.
F of x tilde given theta, right? That is what you are looking for.
Yeah, yeah.
Yeah. So this is both the notations we use. Okay. So f of x
Okay.
tilde is fine.
But so
F of
doesn't they mean different things completely? Like one is saying given x and one is saying given theta.
very good. So f of x tilde given theta means theta is considered as a constant
Hmm.
and x tilde is my observed value.
Hmm. Yeah.
For a particular given theta, for particular observed value, what is my density value? Okay.
Yeah.
Now the adjoint density value. Now this notation L theta given x tilde, or sometimes just written as L of theta, is slightly notational abuse in a sense that it's trying to say that well, my x is completely constant because I have observed my data and nothing to worry about. That is a fix. That is, I'm not going to play with the data. What I'm trying to change here, or trying trial error with different value of theta. So that is why this notation is slightly more popular when people write the likelihood as a likelihood. But both the notation try to say the note. I mean, notational representation try to do the same, say the same thing effectively. But more, this is more probability literature. You will see write it in this way. More stat and ML literature write it in this way. But they're effectively same thing. Okay.
Okay, sir.
Okay. So I'm ignoring these constant part. I'm going to ignore this constant part and I'm going to write this minus half summation xi minus theta whole square uh, plus theta minus mu whole square I equal to 1 to n. Okay, are you guys with me? So if I try to solve this, what I will do, I will just basically optimize this, try to optimize this function. My theta map or posterior mode will be just simply arg max of this entire thing minus half x summation xi minus theta whole square plus theta minus mu square, or simply arg mean, same thing, but I'll work with, I'll just add a minus one, multiply the entire objective function with a minus one, and I'll solve it as a minimization problem rather than maximization problem. And I would rather also solve it. I'll basically multiply a minus two, and then the entire thing same as saying minimization this guy of xi minus theta whole square I equal to 1 to n plus theta minus mu whole square. Now I am choosing a spatial case. choosing a special case for mu equal to 0. Then the theta map is equal to simply solving this minimization problem over theta, summation equal to 1 to n xi minus theta whole square plus summation plus theta square. Okay. Does this optimization problem ring a bell? Do you feel you have seen it somewhere? Have you heard about this word? Regularization.
Yes, sir.
Where?
In our Madhavan's class. Yeah.
Professor Madhavan's class, right?
Yeah.
So he was definitely trying to solve some sum of squares errors of regression kind of line, and there some parameters needs to be estimated, and then he put this something called penalty, L2 penalty, right?
Yeah.
So this L2 penalty is nothing but a prior equivalent to one-to-one mapping of prior distribution. This method also known as penalized likelihood method. Penalized likelihood method. Okay, why? Because I'm putting a likelihood, a penalty on this. What kind of penalty I'm putting? This exact optimization problem can be solved equivalently as a equivalently. You can solve this problem as exact problem can be solved as theta map arc minimization as minimizing sum of squares of theta xi minus theta whole square I equal to 1 to n, subject to a constraint. The constraint is summation theta I square is less than equal to t. In this case, it will be 1 actually, exactly 1. Or actually, I don't need summation. Sorry about that. I don't need this summation. Just summation theta square is less than equal to 1. This constraint will just suffice. This optimization and this optimization, this constraint optimization, exactly same. You can effectively show exactly same. They're dual of the same problem. This is a sort of this behaves like a sort of a non-Lagrangian constant kind of behavior. It does. What it means basically, I am basically putting a constraint on my likelihood. I'm saying that I have what happens is sometimes you have only one or two observations. Suppose in this, you have very limited of information. Suppose if you have a very limited information, your likelihood will be very flat. Your likelihood is not very informative. At that time, you are basically saying that since I have a limited information, my results are not very reliable. If you come across a problem where my results are not very reliable, that means the system I'm trying to solve is not giving me a solution which is a reliable solution, then typically that kind of problems are known as ill-posed problem. Okay, so if a system does not yield a solution, suppose you can have that many things actually does not yield a solution, or solution is not reliable. That means you have a solution but it's not reliable. Solution is not reliable, or third kind of category, solution is not computationally feasible. Solution is means theoretically there a solution exists, but computationally you cannot even achieve that solution. It is so because maybe it's a algorithm which is in exponentially complex. I mean, complexity is in the exponential time. So solution is not computationally feasible. There are many things can happen. It's not computationally feasible. Feasible. Then the problem is known as ill-posed problem. Ill-posed problem. Okay. So system does not yield a solution at all. It does not have even a solution. Or solution is not reliable. You have a solution, you find a numerical solution or even analytical solution, but for certain reason, the solution is not even reliable. Another is situation, you have a mathematically, theoretically there is a solution, but computationally it is not feasible to attain that solution. Then this kind of problems are known as ill-posed problem. Andrei Tikhonov, a Russian mathematician, 1951 in Russian journal, he first tried to give a solution for the problem. The problem he was trying to solve was, he took a system of equation Ax equal to b, and the solution does not exist. The system X equal to b does not yield a solution. Does not yield a solution. So he proposed a system that saying that instead of solving this system, you need to put a constraint on the system, certain constraint problem. And what he proposed that, okay, I cannot solve this problem. What I will do, I will try to solve this problem instead of, so basically minimizing ax minus b over x does not yield solution. not possible. So what he suggested, well, if I can't to solve this problem, you change the problem, or the problem which you can solve, which is solve minimization of x, ax minus b. But then he said that this is the problem you try to solve. And he said that I need to put a penalty on my x. So x is, my system does not have a solution. So I need to penalize x, or I need to put some constraint on x. I cannot allow x to hover around everywhere in the space. This turns out to be solving minimization of x, ax minus b, such that mod x 2 is less than equal to certain constraint. So it turns out that this does have a solution. Basically, does have after, so if you cannot solve a problem directly, if you cannot solve an optimization problem directly, you solve the constraint optimization. This under certain constraints, you can solve this problem. It turns out under this constraint, which typically we call it L2 penalty, under L2 penalty, turns out this system does have a solution. So that means the solution previously does not have the solution to the resource problem. Now regularize the problem. Hence the word regularization. Okay, any questions, any doubt? So this is the pretty much the relationship you see, that the Bayes solution and the is what, whenever we are looking for a regularized solution, most of the time my experience is people don't understand, but they end up with a Bayes solution. Okay, because effectively on the likelihood you are putting certain constraint, that means you are saying my parameter is hovering only in this region, and then given that constraint you are estimating the parameters, and then that is typically the way turns out to be a posterior mode. And then if you solve it as a optimization problem, then it turns out to be a posterior mode or Bayes estimator. Okay, any doubt, any question? So with this we ends the Bayes estimator, likelihood estimator, the method of estimation. Now we will move on to the section on method of evaluating estimator. Okay. Method of method of evaluating estimators. Achha, before we start method of evaluating estimator, anybody have any questions so far? Okay, if you don't have any questions so far, then we can just start. You can always ask me later as well. So, all right. So we will start with the intuition. The intuition is if you have two estimator, if you have two estimators, say which one you would like to choose, which one you would like to choose. For example, suppose x1, x2, xn are IID normal mu sigma square, then x bar is defined as 1 by n summation xi I equal to 1 to n, and s square is 1 by n minus 1 summation xi minus x bar whole square I equal to 1 to n. And then there is another estimator, say S2 square, it is, let's call it S1 square and S2 square, which is 1 by n summation xi minus x bar whole square. So question is which one I should use for sigma square? Should we use S1 square or S2 square for estimating sigma square, right? So this is my dilemma. So one estimator is suggesting I should divide it by 1 by n minus 1. Another estimator is suggesting I should divide it by n. Which one I should use? So in order to compare the method, so one way of doing it is, why don't we take something called, we take the difference. So suppose if W is an estimator for theta is the unknown parameter, then we take the difference and then we take a expected difference on that. So the problem is sometimes it will be positive, sometimes it will be negative, so it will cancel each other's effect. So we square it. And this typically called mean squared error. And turns out this mean squared error is most used MSE is most used, even one of the most used metric to evaluate an estimator or evaluate the performance of algorithm, many things actually. Okay. Now, so this is my mean square error. There is another concept called unbiased estimator. Unbiased estimator. What is that? Now, if W is an estimator of thing, then expected value of W should be theta. What is the intuition? The intuition is if theta is this is the true value of theta. Theta, actually, this is the theta, and suppose this theta 0 is the true value of theta. Now, since my sample x tilde is a random sample, and W is just function of my random sample. So sometimes W will be here on the left side of the theta 0. Sometimes it will be right side of the theta 0. But on an average, if you repeat the process many times, on an average, W should be approximate. On an average, it should be theta. So that's the idea, and that's called unbiased estimator of theta. Then what is bias? If expected value of W turns out to be theta plus constant, or expected value of W turns out to be some constant time theta, see some positive number, suppose, then W is called biased estimator. Correct? All right. Now, like there is a result. I would like you to try this, that expected value of W minus theta whole square is the variance of W plus W minus theta whole square. In other words, I can say mean square error of theta is variance of W plus bias of W whole square. This is a very important result. I mean, this is a very easy to prove actually. So why don't you, I would recommend probably you to try to do the proof. If you can't, you can always find a solution. There are a lot of solution available on the web. You can look into it. There in the book also, I think in Tasselberger or Mukhopadhyay's book also, there is at least hint must be available. So you can do that. You can look into that as well. But this concept of mean square error is a function of two components, the variance of the estimator and the bias of the estimator, is a very strong concept. And it has very strong implications. And next week we will continue discussion on that. Okay. So if you want, I think, just a minute. Yeah. Okay, I'll put a small reading assignment. Okay. I think it will be nice reading assignment. Reading assignment is Kasselberger, page 330. Mean section 7.3.1, section 7.3.1 on mean square error. The title itself is mean square error, and there is an example 7.3.3 and 7.3.4 on page 331. Okay, so these 2 pages your reading assignment. No, page 332 also, including the example 7.3.5, including 7.3. Example 7.3.5. Okay, so basically page 330 to 332. Page 330 to 332 of Kasselberger. So this is your reading assignment. All right. Any question?
So in this MSc where you wrote this variance plus bias, so is the bias same as unbiased? The thing that you said before.
See,
is the bias same?
If the W, the estimator, is unbiased, then bias will be 0.
Yeah. Okay, so like for an unbiased estimator, MSc will be just variance. That's what.
Just variance of W. Yes. Okay. Correct.
Okay.
All right, guys. Thank you very much for your time. I'll upload the notes right away, and see you on Tuesday for the visualization course. And I have assigned a small piece of code on how to plot a statistics on the maps. Please have a look. We will discuss it on the Tuesday. Okay. All right. Thank you. Thank you very much.
Thank you.
Thank you, sir.
Thank you.